In this work, we present RoboPEPP, a framework for vision-based robot pose and joint angle estimation that leverages embedding predictive pre-training. RoboPEPP's primary goal is to estimate the joint angles and robot pose from a single image. This is valuable in many practical settings such as human-robot interaction and multi-robot collaboration. Existing methods use encoders to extract features from images and downstream layers to predict joint angles and robot pose. However, these fail to fully utilize the rich information of the robot's physical structure present in images, therefore, often struggling with occlusions and truncations, as shown here. To address this, we introduce RoboPEPP, which fuses information about the robot's physical model into an encoder-predictor network using a masking-based, embedding predictive pre-training. Fine-tuning this network with joint and keypoint prediction networks and random input masking further enhances occlusion robustness, while a keypoint-based filtering method handles partial visibility of the robot. This slide compares RoboPEPP's framework with an existing method. RoboPEPP uses embedding predictive pre-training for the model to better understand the robot structure. In the embedding predictive pre-training, robot joint regions are masked, and an encoder-predictor network is trained to estimate their embeddings from unmasked image regions. The network, therefore, learns to infer knowledge about the joints from the surrounding context, improving the network's understanding of the robot structure. The pre-trained encoder and predictor are then fine-tuned along with networks for 2D keypoint and joint angle prediction, with randomly masked inputs for improved occlusion robustness. During evaluation, predicted 2D keypoints are filtered based on their confidence. Predicted joint angles are used along with robot's forward kinematics to estimate the corresponding 3D joint locations in the robot's frame. A PNP solver then estimates the robot's pose using the correspondences. We train and evaluate RoboPEPP on the DREAM dataset, which contains data from the Franka Panda, Kuka Iwa, and Baxter robots. Here, RoboPEPP is quantitatively compared with the current state-of-the-art methods using the AUC on the average distance metric as detailed in the manuscript. RoboPEPP yields the highest scores across all sequences, except for Kuka DR, where it remains competitive. RoboPEPP further achieves the best performance on average in terms of joint angle prediction error and percentage of correct keypoint prediction. Here, we compare the occlusion robustness of RoboPEPP. It shows the highest robustness to occlusion with its performance dropping the least as occlusion ratio is increased. Along with delivering the best quantitative performance, RoboPEPP has the fastest inference speed, averaging just 23 milliseconds. Next, we show some qualitative comparisons of RoboPEPP on the occlusion dataset. The predicted poses and joint angles are used to generate a mesh overlaid on the original image, where closer alignment indicates greater accuracy. Similar comparisons are shown in the following on the Panda Photo, Panda Real, and additional real-world data collected in the lab. In all of these examples, RoboPEPP achieves highly accurate overlays while other methods are less precise, as highlighted by the red rectangles. We show similar results here on images from highly cluttered environments with robot occlusions. Here we see that RoboPEPP achieves more accurate and highly stable predictions compared to other competing methods. A similar comparison on the Panda RS dataset with synthetic occlusion is shown here. Accurate pose and joint angle estimation is key for robot collaboration in shared spaces. RoboPEPP enhances the encoder's understanding of robots' physical models, supporting broader applications beyond pose estimation, including system dynamics prediction and imitation learning. Thank you for watching.